Saxon Algebra 1, Lesson 4. Greetings, my students. This lesson has a nice, gentle name, Review of Arithmetic. That sounds easy, right? And it's not a difficult lesson. It's a lot of review, but it's a long lesson with lots of examples. So buckle in and let's have fun. We want to start with a little bit of theory, and then we'll get into more practical things. And I want to start by defining a couple words for you. And the best way to explain these words, the best way to define them, is through a metaphor. So let me do that. When you were a little kid, you probably learned there's this thing called the alphabet. And you started to learn these letters. As independent creatures, right? You probably learned that, D makes the duh sound, like dog and donut. And those you learned were called letters, right? And then somehow the idea was conveyed to you that the letters could be combined in all kinds of interesting ways to make things called words. Apple, boy, chair, for example, right? These were not letters. They were combinations of letters that had meaning to them, right? The letters are just the letters. But when you combine them in these special ways to make words, according to certain rules that you learned as you learned how to read, these were words. These were ideas. These had deeper meaning to them than just the random letters. The letters were the tools that we used to build the words, but in and of themselves, they did not have meaning. Okay, the same works with numbers. We have what we call numerals. There are 10 numerals, because we include 0 as one, and they are just like letters in that they're important, they're the tools, but they themselves do not convey a ton of meaning. It's when we combine the numbers according to the rules of mathematics that we can start to have meaningful what we call numbers. This is how many feet are in a mile. 10 is how many fingers you have. 365 is the number of days in a year. We combine numerals to make numbers. And just like we have rules for combining letters to make words, we have rules for combining numerals to make numbers. For example, we call this the ones place. We call this the tens place, right? The hundreds and the thousands, right? We know that we can put a 0 in any one of these digits, but you don't put a 0 in the first digit, or that's just weird, right? So we have all kinds of rules that we use to combine numerals in order to make numbers and communicate ideas. Da, 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 da. Beautiful. That's my first definition. Now I want to make another chart for you. This is a chart that we're going to come back to later in the year. It's called the chart of real numbers. And I'm going to draw this picture here to remind you that a real number is any number that can be found on a number line. Oh, wait, that's +1. That's +2. Sorry. All right, so real numbers can be found on a number line. We started with Let me put this in here first. Okay, we start counting when we are little tiny babies. Usually someone starts doing it for us, and then we learn how to do it ourselves. We count our fingers or our toes, right? I bet there was a day when your mom wrapped you up. She gave you a bath and she wrapped you up in a bath towel when she was sitting with you on her lap, and she started counting your little piggy toes. And she said, 1, 2, 3, 4, 5, and then she switched to the other foot and she kept counting. Those are called the counting or natural numbers. All right, it's a set of numbers that we often refer to for lots of interesting reasons, and we call them the counting numbers. Later, when you got a little older, one day you probably put your hand into a cookie jar and you felt around and you realized there was nothing inside of it. And that's when you advanced to the topic of whole numbers, because you understood the concept of zero. And that's what makes the set of whole numbers different, is that it includes the concept of zero. So the way we're drawing this picture is to indicate that the whole numbers include the counting or natural numbers with the addition of one more idea, which is zero. Okay? After that, somewhere along the line, maybe when you borrowed some money from somebody or somebody borrowed some money from you, you came up with the understanding that there was a thing called negative numbers. That instead of being broke, you could be in the hole, so to speak, right? If you borrowed $5, you didn't have any money, so you borrowed $5 from your mom, but you were expected to pay her back. Now you have less than $0. You have negative $5, right? Because you owe some to your mom. So integers include the whole numbers, include the counting numbers, but also include what we call the negative numbers. And of course, they go on to infinity in either direction. So that was your next leap of understanding, and that's the next category that we use. The next thing happened when you got to, well, I'll tell you what. If you have siblings, you learned about this earlier, because you learned that sometimes you have to take something up and divide it into smaller pieces, right? If there's only one brownie left and you have 3 siblings, that means you need to learn how to divide that into 4 pieces. And so you learned about fractions, and you learned about decimals, and maybe if you were fancy, you even learned about percents, because all of these ideas are included in rational numbers. A rational number is one that can be expressed as a fraction. So it includes fractions, but it also includes decimals, because decimals can be expressed as fractions, right? We can translate, and percents are the same. We can express them as fractions. So fraction is the key word for rationals. Any number we can express as a fraction, including numbers that have repeating decimals. Okay, at the end of Algebra 2, we're going to come back and talk about how exactly you can prove that numbers with repeating decimals can be written as fractions. Just trust me now that we can. Okay, now these are all real numbers. It's a growing way to categorize them. Over here we have some other numbers that are still considered real, but they cannot be expressed as fractions, and they are called the irrational numbers. They are numbers that have infinite, non-repeating decimals. Okay, so there's no pattern to their decimals. They just keep going and going. And here are 2 perfect examples of that. Pi, as you know, is 3.14, and we usually stop right there. It's called truncating the decimals, but they keep going. They just keep going, and there's no pattern to them, and they're just random, and it's crazy. Square root of 2 is another number. There is a number that multiplied by itself equals 2, but it has infinite non-repeating decimals. So we don't try to write it as a number, we just write it like that. Okay, so there are these things called irrational numbers. They're still real. We can still put them on a number line, right? This is 3.14 and then a bunch of little things after that. But we can still graph it. It just doesn't, it just has that infinite non-repeating decimal, and it can't be expressed as a fraction. That's what makes it a separate category. All right, now oftentimes students listen to me talk about how real numbers are those that can be found on the number line, and there's usually a smart alecky boy in the room who says, oh yeah, is there the opposite? Like, what's the opposite of a real number? Is it like an imaginary number? Yes, that's exactly right, and we're going to learn about those later. So I'm just going to add them to our page here. I'm going to turn this. There is a thing called imaginary numbers. They're expressed with the letter I after the regular number, and they are numbers that cannot be found on the number line. Huh, who knew, right? So what I want you to do is not memorize this, but to start to get familiar with it. We're going to come back to it later in the year, but what I want you to know is that these names, counting numbers, whole numbers, integers, rationals, irrationals, they have specific meanings. And we're going to get more familiar with them as we go, real numbers, imaginary. But for now, I'm just throwing that out there for you to think about. Okay, I think that's enough. You know about number lines. All of that is fine. Let's go move on to some problems. Shall we? All right. First, John is going to push us through a bunch of multiplying and dividing fractions. Ready? And he letters these, so I don't know what to say about that. Remember that when we add or subtract fractions, we have to make the booties match. But when we multiply, we don't have to deal with any of that. We just multiply straight across the top, straight across the bottom. If we can cancel first, we do that. We'll get to that. But for now, just the basic operation is straight across the top, straight across the bottom. In my brain, I always see those arrows. Okay? Easy. John converts things like this to mixed numbers. No, you can leave them as improper, always. All right, what about if we do division? Later, we're going to explore more about why this is so. But when we divide with fractions, what we do is we turn it into a multiplication problem. I'm using a dot, here I'm using an X. Either one works. We turn it into a multiplication problem by flipping the fraction that comes after the division sign, right? So it's the one that comes after. And then we just multiply straight through. 32 over 45 is the final answer here. We can't reduce that. Notice that here we could have reduced, right? 4 to 8, 3 to 5. We don't know. We can't. We can't reduce until we change it into a multiplication problem, all right? So, or cancel, if that's the way you think of it. Those two words are kind of synonymous. We don't do that first. First, we flip it. Okay, so that's important information. Flip first. C. 7 over 3 times 30 over 9. Okay, now we get to practice some canceling. Remember that when we cancel, it always has to be top to bottom. We can do the same fraction, we can do opposite, but we can't do bottom to bottom or top to top. All right, so in this case, there's a couple ways we could go, but the most obvious thing that occurs to me is to do 10 and 1. We're dividing both of those things by 3, right? So then we can multiply through and get 70 over 9. all right? It's okay if you forget to cancel. It's okay to just multiply through. Like, let's pretend we forgot. 210 over 27. And if we would have been thoughtful, we would have realized, oh shoot, that can be reduced, right? And we would have had to figure out how to reduce it and go on from there. That's why it's easier to cancel when the numbers are small. Once we multiply them together, it turns into a big mess. So canceling is a cool way to go. D. Oh, what about three-part multiplication? Well, the good news is John usually has a lot of fun with giving us lots of things to cancel in these. So we have the fun of doing that. I'm gonna say, let's cancel the 5s because they both go to 1. And then let's do the 3 to the 6. I have 1 left there and I have 2 left there. I can make those both as 1s, okay? I could have canceled the 6 and the 21 by dividing each of those by 3, right? 21 divided by 3 is 7. 6 divided by 3 is 2. I could have done that, but here's the fun spoiler. It doesn't matter. As long as you're reducing or canceling accurately, it doesn't matter which patterns you use. Okay, so now I've got, let's see, I've got a 1 and a 1 and a 21 in the top and a 1 and a 2 and a 23 in the bottom. When I've done a lot of canceling like I did here, I like to circle what's left so I don't get confused. But now I can see that my final answer is 21 over 46. Yay. I have to smiley face everybody. Okay, E. Still in the same category. 2 1/2 times 5 1/3. Okay, I told you that sometimes in adding or subtracting fractions, it's okay if you want to leave them in mixed numbers. When it comes to improper, or when it comes to multiplying rather, or dividing, which we're going to do in the next example, always switch it. Always switch it to an improper. Gracie's sleeping, but she's wagging her tail. It's really cute. Good girl, Grace. Good girl. She's sound asleep and her little tail's wagging. Okay, so in a multiplication or division, we always switch to impropers. So remember how we do that? We multiply the bottom times the big and add the top. 2 times 2 is 4, plus 1 more is 5. And then the denominator always stays the same. Times, bottom times the big, 15 plus 1 is 16. Denominator stays the same. All right, the reason we do that is because we want to cancel as much as possible, and we don't have a way to cancel using mixies. So 2 and 16 I can cancel. 1 and 8, right? And now I'm ready to multiply through. 40 over 3. John very often takes an answer like this and converts it to a mixed number. For example, he shows the answer to this is 13 1/3. How do we know if it's the same? Take John's number and convert it to an improper. 3 times 13 is 39, plus 1 is 40. 40 over 3, check. Okay? F. This one's similar, but it's a division problem. 12 1/3 divided by 2 1/6. That looks really scary and hard, but just follow the steps. Convert these to impropers. 3 times 12 is 36, plus 1 is 37 over 3. 6 times 2 is 12, plus 1 is 13 over 6. Now we flip. We flip the fraction that comes after the division sign. I don't try to cancel now, right? We flip first and then we cancel. So that becomes 37 over 3 times 6 over 13. Flip first. Now we can cancel, and I can get the 3 to the 6. 37 is prime, 13 is prime. Once you know a number is not at prime, unless another number goes into it perfectly, we're not going to be able to break it down and take a little piece out of it, if that makes sense. So then my final answer becomes 2 times 37, which is what, 74 over 13. Mixed numbers not necessary. G. G looks really hard, but I want to make sure you see how not hard it is. Oh, I wanted to say one thing about that previous problem. Okay, finish copying G. Allow yourself a minute to freak out if you think that looks really hard. Going back to this number, this one I said, if you feel comfortable, you can start doing some of these things in one big step. For example, with this one, you could say, okay, I need to convert and flip. So I'm going to convert this to a mixed number, convert that to a mixed number, flip it, and change it to multiplication all in one step. You basically would block that out, and you'd go, okay, 37 over 3 times, and then you'd go, okay, it's 13 over 6, but I'm going to flip it, so it's 6 over 13. It's okay to take the shortcuts like that if your brain feels comfortable. If your brain says, no, that's too many changes at once, I want to change one thing and then the next, go for it. First, convert. Convert to a mixed number. Then flip to a multiplication problem. And then cancel. And then multiply. Those are the 4 steps. Steps for dividing mixed numbers. If you feel at all overwhelmed by this process, go ahead and copy that list. Okay, it's what we did here. Convert it to a mixed number, flip so you can multiply, cancel, and then multiply straight across. All right, this is just another way to format a division problem. Remember that a fraction line always says divided by. So this problem is really nothing different than this problem, right? 3 1/3 divided by 2 1/5. 3 1/3 divided by 2 1/5. This is the same thing. So if you see this, don't panic. Just remember that that sentence will speak to you, and go ahead and rewrite it in this format. All right, I'm going to do what I just talked about. I'm going to convert these both to mixed numbers, and I'm going to flip it into a multiplication problem all in one step. Ready? 3 times 1 is 9, or I'm sorry, 3 times 3 is 9, plus 1 is 10. Denominator stays the same. Now I'm flipping it to multiplication. I'm using a dot. 5 times 2 is 10, plus 1 is 11. That goes down here, and then the denominator goes up top, right? 5 times 2 is 10, plus 1 is 11. I put it on the bottom, and then I put the old denominator up here. Now I've flipped and converted in one step. Sadly, there's nothing that I can cancel here. It's so sad, right? But I can't, and so I simply write the answer is 55 over 33. Oh no, 50, sorry, not 55. I was looking at that 11. 50 over 33, that's the correct answer. Cool, right? Okay, that is a lot of multiplying and dividing of decimals. And we have already reviewed adding and subtracting. So we're cool. A little bit more theory. Talking about symbols. You know that means equals, right? It means the things on either side of the sign are the same. This is a fun one. 5 plus 2 is not equal to 11. So we can write it like that. It's kind of like the traffic signs, you know, that are like this. It's the same idea. Cross it out means I don't do it. Addition, subtraction, multiplication, and division. I just want to give you some words for this. In an addition problem, the answer is called a sum, which is usually pretty easy to remember. The two numbers that we're adding are called the addends. So the addend plus the addend equals the sum. With multiplication, it's factor times factor equals the product. Subtraction, there are special names. I guess I'll tell you. I don't want to confuse you, but you don't really have to worry about this. The first number, the bigger number, is called the minuend, and the smaller number is called the subtrahend. I mean, no one knows those words. This is important though. The answer to a subtraction problem is called the difference. Okay, that's important to know. These words are all useful to know, but these are for children. And then in division, it's dividend is the big number divided by the smaller number, which is the divisor. And the answer is called the quotient. Okay, and another way to write that is dividend divided by divisor. Again, quotient is a good word to know. Divisor and dividend are not that important. Okay, but just sort of shove those in the back of your mind. All right, let's review decimals. Adding decimals is nice and easy. Now John's decided he's going to actually number our problems. Add, and I'm going to give you two numbers here, 4.0016 and 0.0. And I've done the important thing as I wrote this down. The important thing when we're adding or subtracting decimals is to line up the decimal places, right? It doesn't matter if they have a different number of decimals. Do this first. Then if you want, you can fill in with 0 so that they have the same number. But the most important thing is just to line these puppies up. Now we just add happily. And we don't have to pay any more attention. We just copy the decimal into the answer. That's correct. Okay? So the secret for adding and subtracting decimals is line them up. Let's do a subtraction one just to practice that lovely feature. Subtract one number from another number. The one that's written that way. This is the number. When this is the way we say the problem, this is the top number and this is the bottom. This is the minuend and this is the subtrahend. No, I don't like that. This is the number you put on top. This is the number you put on the bottom. So I'm going to use that information to write this properly. 4.0016 and subtract from it 0.0. I think these are the same numbers we had in the last problem. Yeah, they are. But this time we're subtracting. Same rule though. Line up the decimals, Fill in with zeros if you like. You don't have to. I mean, in subtraction, it makes a little more sense, but put the decimals in so that they're lined up. Now we can subtract. Right? Remember borrowing? You've probably been doing that long enough now. Now here is a tricky one, right? We have a 0 here. We need to subtract 1. We need to borrow, but look, we have to go way down here to this 4. That becomes a 3. Then we turn that into a 10. Then we borrow against the 10, 9. We turn that into a 10. We borrow against that to make it a 9. And then finally, we turn that one into a 10. 10 minus 1 is 9. 9 minus 2 is 7. 9 minus 0 is 9. And then 3. That's the right answer. Hopefully I'm not going too fast. I'm assuming that once I remind you of the rule that this gets pretty easy pretty fast. This was example 4.2. Okay, so that's adding and subtracting decimals. Just line them up. Now let's talk about multiplying decimals. Multiply 4.06 times 0.016. When we multiply, we don't need to line up, okay? I'm going to make a little list here. When we add and subtract, we line up the decimals. And if needed, we add zeros. Okay? That reminds me of 0 in the movie Holes. Have you guys watched the movie Holes? You should. It's so good. It's a Disney movie, right? Back from, I think it's from the noughties. It's from the early 2000s. It was in my kids' childhood. Great book, great movie. Okay, when we multiply decimals, we ignore the decimals. We multiply, and then we count This is confusing. So write it down and then I'll explain what I'm really saying. When we're multiplying, we ignore the decimals, we multiply, and then we do the counting thing to figure out where to put the decimal in our new number. So let's do that. Let's ignore the decimals and just multiply. 6 times 6, 36. That's 3. And then 24. And then 6, 0, 4. And now notice these two zeros, we don't need to do anything with those, right? We don't need to multiply with those. We just multiply by the 6 and the 1. Here, let me put a 0 here to be my placeholder. Now we add, right? 6, 9, 4, 8. Now, here comes the last step that gets really wordy and it's hard to explain. We go back to the numbers, and I like to underline all the digits that were behind a decimal in the original numbers, all right? So there's the decimal, so these two are behind it. There's the decimal, so these 3 are behind it. We count them up, 5, and then in our product, we have to make sure that we have 5 digits behind the new decimal. So we count from here. 1, 2, 3, 4. We need one more place before we can put the decimal in and have 5 behind it, right? So that means we add a 0 right there. Weird, right? If you want to add one here just for looks, that's fine, but that would be a fine answer too. So that's what I mean when I say count number of digits to locate the new decimal. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. We had to add that 0. That's correct. It's so fun, right? Example 4.4. Division. Oh my gosh. The rules for dividing decimals are crazy. Let's do one, and then we'll talk about the rules. Divide blank by blank. How do we know how to set that up? If we're doing long division, which we're usually doing in this, the first number goes inside the division box. The second number goes outside the division box. So let's do it right here. There's our division box. John says divide 6.039 by 0.03. Okay, so that's how I know how to set that up. There are the decimals. Now, here are the rules. If there is a decimal in the outside number, we have to bump it all the way to the right. 1, 2. So I'm going to say bump outside decimals. And then I'm going to say copy to inside. And I'll tell you what I mean by that. If I move it twice here, I have to move it twice here. And then our last step is to bring the decimal up. And I'll tell you what I mean by that. Our decimal's here, right? We had to bump this one twice to get it to bump it out. Then we have to do this one twice to copy, and then we bring it up to the answer. Okay, so that's what I'm hearing. Bump the outside decimal, copy to the inside, bring the decimal up. Okay, it's hard to say this in a concise way, and I don't want you to write a small novel to try to remember this. Those words help me. If you want to describe it differently to yourself, do it. Okay, now we've got the decimal located properly, and we can ignore all of this nonsense because it's not really part of our problem. And we can say 3 into 6 goes twice. That comes out perfectly. So when we subtract, there's nothing left there. There's nothing there. Bring down the 3. Oh, it goes in there once. 3. We subtract. We get another 0, but we bring down one more 9. 3 into 9 goes 3 times. Now, what do we do about this answer? We fill in a 0 for the missing digit. And that's correct. Yay. Next topic, unit multipliers and conversions. Oh my gosh. A unit multiplier is simply a fact. It's a way to connect two ways of measuring the same thing. Okay? So, for example, we can measure something using feet, or we can measure it using inches. A foot is bigger, so for every 1 foot, we know we're going to have 12 inches. But those are two ways that we can measure, right? They're two ways of measuring the same thing that are equal. For every unit multiplier we can think of, we can turn it upside down and make it find its partner. For every 12 inches, there's 1 foot. I just flipped this upside down. Now, I used to think, this is stupid. Why do you have two that are exactly the same? That makes no sense. Well, they're useful in different ways. One of them is useful if we're trying to convert from feet to inches. The other is useful if we're trying to move from inches to feet. So they do both serve a purpose, just only in a context, okay? So this is what a unit multiplier is. We use them when we are converting lengths. So let's look at a problem like that. Use 1 unit multiplier to convert 32 feet to inches. This is how I set up my problem. This is where we're starting. This is where we end up. John tells us we're going to multiply it by 1 unit multiplier. So I draw a box where I'm going to write that in. It's going to be a fraction, and then when I multiply it, that will give me my answer in inches. So what I have to do is I have to figure out what is the connection between feet and inches. Well, luckily I happen to choose it right here. And by the way, I just thought of this one. It just turned out that way. If I'm trying to change feet into inches, which is what I'm trying to do with this box, I write it here because sometimes we'll have multiple boxes and we'll be doing different things in each step. It kind of seems like overkill here because we already know we're trying to go from feet to inches. But you'll see when we get more complex problems, it helps to write what you're trying to do with each box underneath it. Now, we know that these are the two multipliers that connect feet and inches. So one of these is going to be our buddy. How do we know which one to choose? Choose the multiplier with the starting unit on the bottom. It's a non-mathematical talk, but I'll tell you what I mean. We have two to choose from. Our starting unit is in feet. That means we want to choose the multiplier that has feet, our starting unit, on the bottom. That would be this one, wouldn't it? So that's the one we're going to use here. 12 inches for 1 foot. Now, the reason we want to do it that way is because we want the starting unit to cancel. By putting it on the bottom, I'm setting up a situation where I'll be able to cancel those. Now, once we multiply this, our answer will be in inches, and that's exactly what we want. So our answer then is 32 times 12. I'm using parentheses to show multiplication. And in these problems, it is not necessary to multiply through. We just show the components. And that is the right answer. All right? This is super important. Knowing how to create the unit multipliers is super important. And then knowing how to decide which one to choose is the other super important thing. We're going to do a handful more of these problems, so you will get an opportunity to practice, as will I. I'm getting some cool shadows on my page. I hope you can see okay. All right, 4.7. No. 4.6, sorry. I was trying to skip a problem. Use 1 unit multiplier to convert 36 feet to miles. And then John very helpfully tells us that 1 mile equals 5280 feet. Now, I want you to memorize these. Break this one in your book if you don't have it already. Some of them you already know, like you probably already know that there's 12 inches in a foot, like we just did. This number is a little harder to remember. Write it down. Keep it in mind. You can always Google it if you forget it, but you'll need to know that in your life. All right, so in this box, we're going to go from feet to miles. There's the relationship. So we know there are 2 multipliers. It's either 1 mile for every 5280 feet, or we can flip it, 5280 feet for every 1 mile. Which one do we choose? Oh, we choose the one that has the starting unit in the bottom, this one. That's the one we want because we want those feet to cancel. That's how we can tell. 1 mile, 5280 feet, yay. We're going to start doing more and more of this part of the work in our heads, but I want you to be really clear of how I'm doing this. All right, now we're multiplying this. Some students like to put that over 1 just to make it all neat and tidy. And we can cancel our units. Feet cancel, and now we're writing about miles, and that's what we want. So our final answer is 36 over 5280 miles. And again, John does not expect us. In this one, he gives us a simplified answer, but you never have to simplify it for me. That's great. Example 4.7. Use 1 unit multiplier to convert 47.25 inches to centimeters. And again, John is helping us out. He tells us that 1 centimeter equals, no, 1 inch equals 2.54 centimeters. This is another one you should write in your book. That's a 1 inch. Okay, equals 2.54 centimeters. So now we have our we'll be able to create our multipliers. We know we're gonna multiply this. It says inch, it's kind of messy. We can put it over a 1. We can draw, the unit multiplier is always a fraction. So I think in terms of, I'm gonna put a fraction in there. It's gonna be the fraction that takes me from inches to centimeters. Again, that's obvious in this problem, but in others, this kind of note will be helpful. Our choices are 1 inch for every 2.54 centimeters, or we flip it and write the centimeters on top. Okay, those are our two choices. Here's our starting unit. We want to choose the multiplier that has the starting unit in the bottom. So that's this one. And again, that will allow us to cancel. 2.54 centimeters for every 1 inch. The inches cancel, and so my final answer is 47.25 times 2.54. I can ignore the ones in these answers. It's not necessary to write all the ones. Sometimes John does, and I disagree with him on that. I think it just clutters up the answer. Okay, all right, let's try one more of these. And this time we're gonna try doing some of this work in our head. No, we're not. Not yet, because I'm throwing another curveball to you in this one. We'll get to that. We'll eventually do more of that in our head. Second, I want to move my book down so I'm not so much in the shadows. Because I know that's harder for you to see. That's what happens when I record in the afternoon as the light changes. Okay, this will work. Grace is still sleeping. Okay, this is example 4.8. Use 1 unit multiplier to convert 42 meters to centimeters. This time, we're not using English units, we're using metric units. They work exactly the same, so it's not different, but that's the curveball in this problem. 1 meter equals 100 centimeters. The lovely thing, put this in your book, in your notes, the lovely thing about the metric system is that they don't have weird numbers like 2.54 and 5280. It's all just 100, 1000 usually. It's one or the other of those numbers. It's a much simpler, more crisply designed system, and that's why the metric system is so cool. Okay, so we want to convert from meters to centimeters. Remember, a meter is about a yard. It's about how far your hands are apart if you place them comfortably far apart. Most dads are around 2 meters tall. A centimeter is like that big, right? A dad equals about 2 meters, and that is like what a centimeter looks like. All right? So 100 of these will make half of a dad. All right, so here's our unit multiplier. Here's where we're gonna write our fraction. It's got its head in the clouds. I'll put this over a 1. In this box, we want to go from meters to centimeters. All right, so our choices are 1 meter for every 100 centimeters, or we flip it. I know it seems redundant, but it does make a difference, right? We want the one that has our starting unit on the bottom. That's him. Up into the box you go. 100 centimeters for every 1 meter. Our starting units cancel, and that gets us right where we want to be. So our final answer is 42 times 100 centimeters, which again is a fine way to write it. My lines are kind of out of whack, but just pretend. These are easy enough that you can multiply it through in your head really easily. If you want to, you can do that, but it's not necessary. to me. Again, seeing the components of how you got the answer, that's more important. 4.9. Okay, now we're going to hit the big leagues. Use 2 unit multipliers to convert 42 feet to centimeters. Now we know we're going to use 2, so we can just, John tells us, so we can just write those boxes in. We're multiplying all of this through, right? Here, we need to go from feet to centimeters. We don't know how to get from feet to centimeters in a single jump, but what we can do is we can go from feet to inches. That's easy, right? 12 inches in a foot. And then we can go from inches to centimeters, because we just had that one. That magic number is 2.54, right? There's 12 here. So what I do is I write down what I want to accomplish in that jump, and I write down the magic number that's there. Now, let's put this over a 1 just for fun. In our first one, we want to go from feet to inches. We know that we want feet to be in the bottom because that's the starting unit, right? So we know feet need to go there so they can cancel. So that means inches have to go up there. I no longer have to write them down. I can carry them in my head. I start by writing in the starting unit down at the bottom because I know I want that to cancel. Then I write the other unit. I know I'm trying to go from feet to inches, so I write the inches up there. Then I ask myself, which is bigger? A foot or an inch? Well, a foot is a ruler and an inch is part of a ruler. So we know there's 1 foot, 12 inches, right? So when I ask myself which is bigger, the bigger one gets the 1 is how I think of it, right? The bigger unit gets to have a 1 by it, and then give the special number to the smaller unit, right? A foot is bigger, so he gets the 1. There's 12 inches in a foot, so the inches gets the smaller number. Now I can cancel my units, and now I'm in inches, okay? That is my new starting unit, because that's what we're starting from. So now when I go to do the second one, this is what I consider the starting unit. So now I know, okay, I want inches down here, so that will cancel. That means centimeters needs to go up there, okay? Then I can cancel. I like to do that before I get my numbers in so it doesn't confuse me. Which is bigger, an inch or a centimeter? An inch is bigger. An inch is about like that, and a centimeter is about like that, roughly. Okay, so that means 2.54 goes here. Okay, that's the way you can shortcut these problems a little bit and carry more of the work in your head. Now I just need to summarize. That's equals. There isn't room the way I wrote this, so I'm going to write it down a little lower. It's 42 times 12 times 2.54 centimeters is my final unit, right? That is a perfectly lovely way to write it, and that's the right answer. Cool, right? Let's do another one. Oh, the light's finding me. This is our last problem, by the way. Thank you for being patient. This was a long lesson. Use 2 unit multipliers to convert 4 miles to inches. Okay? It's nice when John tells us how many we need because we can draw out our boxes and get everything set up before we have to start worrying about numbers. 2 unit multipliers. Put that over a 1. We need to go from inches. I don't know how to go from miles to inches directly, but that's okay. We don't have to. I do know how to go from miles to feet. And I'm going to write down that number. That's 5280, right? That's the big number there. And then I'm going to need to go from feet to inches. Oh, and I know that. That's 12, right? That's the number of inches in a feet. Okay. So now I'm ready to start filling in my multipliers. There's my starting unit. So I know I want miles on the bottom. That means I have to put feet on the top. Which is bigger, a mile or a foot? A mile, so it gets the 1, and then that means foot gets the special number, 5280. Okay, so there are my notes. Here's how I use them to fill this in. I cancel, and I see now I have a new starting unit of feet. Okay, so when I go to do my second multiplier, feet go on the bottom. Yes, I want to cancel. That means inches goes on the top. What's bigger, a foot or an inch? A foot, so it gets the 1, and then there are 12 inches. In all 4 of these examples that I've done, we always end up with the 1 in the bottom. That's not necessarily going to always be true. That's just the way these problems have worked out. But the 1 can be in the top just as easily as the bottom. All right, so don't think that that's how it always works. All right, now our feet cancel, and we're left with inches. And look, that's where we want to be. So yay, we did it. We accomplished it. Now we just have to summarize our numbers. And again, I'm going to go down a little because I feel crowded up there. 4 times 5280 times 12 inches. That is our final answer. And that's perfectly formatted. That's just the way I would like to see that answer written. I want the unit, but you don't have to multiply. Yay! Okay, John gives you, at the very end of this lesson, a list of some of the key values, the unit multiplier information that we will need. So you might want to copy this into your cover of your book where you keep your formulas, or you might want to put a little flag on this page, one of those Post-it note flags, but this will be helpful to you. Okay, so for the last time, you are doing all of the practice, and then you're doing either the evens or the odds one day, and then the next day, let me show you. So here's 4, right? I would say the first day do all the practice and then the odds, let's say, and then the second day you'll do all the evens. Next week we will be on a more normal setting. Thank you for lasting through this marathon lesson. I hope you feel good about it though, because I hope it was all nice review and you feel smart and you're ready to go. All right, thank you all. Video chat with you soon. Goodbye.